Good morning. So let's see. Let's do a little fast inverse square root stuff here. Let's step through this algorithm and see if we can understand it line by line.
Inverse of a square program myself out. So it's 759.
This line right, this code right here. So copied and pasted into this C++ Jupyter kernel thing. Got this from Wikipedia. Oh well, let's see if it's exactly the same. Yeah, it looks the same. X2, Y. Yeah, it looks like it's straight up the same. It looks good. Let's see if this gives us the number that we think it should. Fast inverse square root of 2. So let's see what we think that should be. Oh, how about 4? Like a more round number. Okay, that seems like it should probably be close. Let's just verify. So this whole thing is computing the inverse square root. So it's doing 1 over, it's doing 1 over the square root of number. So if we do inverse square root of 4, that would be 1 over the square root of 4 is equal to 1/2, equal to 0.5. And so this thing is close to 0.5. So we kind of verified that this is doing 1 over inverse the square root. And so what would be the next thing? It's like if we do the inverse square root of 16, 1 over the square root of 16, 0.25. See how close this thing gets. This. Kind of close. How do you actually think of how close numbers are anyway? Like, how close is like 0.25 to 0.24? 9577. I want to ask ChatGPT. Error rate, relative error. How large the difference is compared to the reference value. The error is about 0.1692. Let's see what this actually means, though. So it's the true value minus the approximate value over the true value. So this is the approximate value. Do this. Need semicolons. Okay. So if we do, let's see. Yeah, let's just do 0.25 minus approximate value. Divided by 0.25. So you get this. So yeah, so how do we intuitively think about this? So this is the difference. It's like how far it is away divided by the true value. Well, I guess we could kind of using the units or whatever here. I guess, yeah, this thing gets multiplied by 100. Yeah, times like 100%. But if we just kind of think of in terms of like 0 to 100, pick some nice round values. It's like if the approximate value is equal to the true value, so you basically have like the true value minus the true value over the true value. So that would be equal to 0. So I guess we would say we have a 0% error rate. And what if the approximate value was double the true value? So, yeah, I don't know. I think we're gonna get like, okay, yeah. Let's just do that. So we got the true value. Maybe let's just do like true minus approximate over true. So we'll say that what if A is equal to 2 times the true value? Taking the absolute value of this. So we got 2 minus 2t over t. So this is equal to negative t over t, which is equal to t over t, which is equal to 1. And we multiply this by 100%, and we say that in this case, the error is 100%. So if the approximate value is double the true value, then the error rate is like 100%. If the error rate is half of the true value, then we would say the error rate is 50%. If the approximate value is, say, 4 times true value size, then yeah, it's the error rate is 400%. So maybe we could like graph that a little bit. So so here we have I guess on this axis we have it's basically the numerator here. It's like the difference, the absolute value of the true value and the approximate value. Did ChatGPT call it something? said the absolute error. So down here we have the absolute fucking error. So we said, yeah, and then on the y-axis we have the error rate. Is that what it said? It's the relative error, percentage error. The relative error, I guess we'll say it's the percentage error. So yeah, we got 0 here. Say we got 100%. So if the absolute error is 0, then we get 0. If the absolute error, let's say, is 1, then we get 100% error. If the absolute error is 0.5, then we get 50% error. If the absolute error is 2, then we get 200% error. And so, yeah, this graph is basically just kind of like a straight line. Just kind of like, yeah. So just trying to get some intuition for, yeah, the error calculation here. So, yeah, to say that we have a point, what is it? A 0.1629% error, 0.1629% error. That's pretty good. It's pretty good. I mean, if you just had a 1% error, what would a 1% error be? It's a little hard to think of it in absolute terms. Basically, the absolute error has to be 1/100th the size of the true value. 1% of the size. Yeah. So then basically the approximate value is just like a 1% different. It's just 1% off. Yeah, because you kind of think of like a line thing here. Say we got the true value here. And so say this is like 2 times the true value. Let's say like this is 0. And so, yeah, if you break this up into chunks of like 100, there's like 100 of these things. Then if you're basically right here at the first one, which is the 1/100th, it's true value plus 1/100th. This is your approximate. Yeah, then your error rate, then your percentage error would be 1%. Yeah. Okay. Okay. So for this thing to be 0.1629%, so we just talked about 1%. This is a tenth of that. So you basically take like 1% of 0.25, and that's like some number, and then you take a tenth of that, and that's how close this is, basically, this approximate value. That's pretty dang close. It's like 0.24 or something. All right. So that was a little diversion. So yeah, we can kind of go step by step through this function. One way to kind of do it out is to kind of just take this function and, you know, just kind of break it up line by line. So we say like number is equal to 4, this. And so there you go. Got some constants. And x2, y. Let me kind of start doing this stuff. Let's just kind of do it and see like the values that we get. Yeah, I don't know if I'm gonna like do this first thing right now. I think I just wanted to kind of like, I don't know, that was like a fun little excursion on relative error, no, percentage error calculation. Yeah, I think I'm kind of satisfied with that. I think I'm gonna end this stream. All right, see you guys. Peace.